Good morning, everyone. Can you hear me?
Yes.
Okay, great. So we're excited to start the morning session of our conference. And the first talk would be from Aleksandr Mokeev, non-commutative operator graphs generated by POVMs. So, Aleksandr, I'll give you the floor.
Okay. Thank you. At first, my great thanks for organizers for this opportunity to participate in this conference. Title of my talk is Non-commutative operator graphs generated by POVMs. This talk based on joint works with Grigori Amosov and Aleksandr Nikolaevich Pechin. This work was supported by grant of Russian Science Foundation and performed in Steklov Mathematical Institute. Okay, at first I want to give a definition. Non-commutative operator graph is a subspace in space of all linear bounded operators on the Hilbert space H. Also, non-commutative operator graphs called operator systems. It is a subspace with following properties. Identity operator lies in this subspace, and it is closed under operator conjugation. These systems play the role in quantum error correction theory. To explain it, I need to give some more definitions. Quantum noise and error correcting codes. Let me have two quantum systems, A and B, with connected Hilbert spaces HA and HB. Then the set of completely positive trace preserving maps are defined by set of operators Vj with the following property, such sum equals to identity operator on HA, and the set of completely positive trace preserving map defined by this set in such way that Krauss operators lie in linear envelope of Bj set, and this set of completely positive trace preserving map is a model for quantum error. For set of quantum errors, I will call it informally quantum noise. And to define a correction operation, we need a subspace in space HA and another completely positive trace preserving map decoding channel such that for each error delta and for each element of code, for each state of code, the following equation holds true for some constant C delta. Okay. With each set of with each quantum noise, better to say, connected unique operator graph given by this rule. And here immediately appears in our problem, if we have abstract operator graph, how to find the noise to which this operator graph is corresponding to. it's possible to prove that for each operator graph is at least one quantum noise, that this graph is associated with that noise. But if we have...
By the way, what is operator graph?
Oh, I don't hear you. I don't hear your question well. Could you please repeat it?
The definition of operator graph was done on the first slide.
Yes, yes. And then we give the definition of operator graph corresponding to quantum noise. And it also generated, it's also obtained from these operators B. Okay. But here appears one problem. Say if we have a graph, for example, parameterized by some generating set, the graph, then the graph is a closure of linear envelope of some generating set. How to describe the noise that corresponding to that graph is such abstract problem. Okay. What role operator graphs play in this quantum error correcting theory? There is a sufficient and necessary condition of Kneel and Laflamme. Let we have operator graph corresponding to noise, then the subspace S will be a quantum error correcting code for the noise if and only if the following condition, the following equation holds true for orthogonal projection on code and for this graph. So we see that we can pose the problem of existence of quantum error correction code for abstract graph, not for noise, not only for noise, but also for operator graphs given in some abstract way. Also, it is necessary to mention that projection on code called anti-click, and we also interested only in non-trivial examples, then the dimension of the quantum error correcting code is at least 2. Okay, as I say, problem of existence of quantum error correcting code could be posed for operator graphs. Here is some results. For example, result of Kneel, Laflamme, and Viola. Let we have n-dimensional Hilbert space and the operator graph on this space, and if such inequality holds true for some natural number, then the graph of such dimension always have the code of dimension k. We see that here the dimension of the graph is something like square root of the dimension of the space, not of the space of operators, that is n squared. But also here I can mention our result, our example in the Hilbert space, that is the tensor product of two n-dimensional spaces, it is possible to construct a non-commutative operator graph of large dimension which have an anti-click pk. It's a different situation to that sufficient condition. Okay. Now let me give the definition of positive operator valid measure. Let we have some set and with the sigma algebra of subsets and the set of positive operators on some Hilbert space called positive operator valued measure if this mapping on empty set equals 0 operator, if of all whole set it equal to identity operator, and it countably additive. Okay. Easy to see that that such closure of linear envelope of POVM is an operator graph. We have it contains identity because of the definition of POVM, and because of positivity of M of B, it's closed under conjugation. And also it is possible to show that any non-commutative operator graph is generated by some POVM. So it is such, it could be called the universal method of parameterization, maybe something like that. Okay, so we can study that problem for special cases of POVMs. Consider the special case when this set is a compact group G with some higher measure, with unique higher measure with such normalization, and the sigma algebra is the sigma algebra generated by compact subsets of a group. And let also we have continuous projective unitary representation of our group in some Hilbert space. Then we can define the action of the element on the operator by this rule. And let we have POVM on this Hilbert space, and this POVM called covariant with respect to the action of this group if the action on the element of POVM is the element of POVM, the element corresponding to left translation of set B. Okay. In finite dimensional case, each POVM is known to have such form of the integral with density defined by some positive operator. So the graphs which are linear envelope of POVMs will take such form with this positive operator and representation. Okay, for such POVMs generated by covariant, for operator graphs generated by covariant POVMs, it is possible to define sufficient conditions of correctability. Let we have finite dimensional Hilbert space, and some covariant POVM. Consider spectral decompositions of operators of our representation, and let graph V is generated by our POVM. Suppose that one projection on the eigenspaces is constant for all operators of representation. Then this this projection is a quantum anticlick for graph generated by covariant POVM, and also the want to rank be non-trivial. Okay, but how to describe how to solve this back problem and describe errors to which operator graph generated by POVM is corresponding to. Here we can offer maybe a little bit weak solution for this problem, but it's what we have. Okay, consider an operator graph generated by some POVM when by Dirac theorem we have the dilatation for some projection valid measure on the larger Hilbert space K, our POVM could be represented in such way. Consider the set of completely positive maps given by such expression, and then the non-commutative operator graph generated by our POVM is the graph corresponding to the errors generated by these completely positive maps. Okay, then I want to discuss some examples. First example is example for Jaynes-Cummins model. Let we have two-dimensional system with state space HS, and it is coupled with the field given with the state space HF. Then Jaynes-Cummins Hamiltonian acting on this space is the following Hamiltonian. Omega S and omega F is the frequencies of atom and the field correspondingly, and sigma Z is the Pauli matrix, and sigma plus and sigma minus is rising and Lagrangian operators, and A plus and A minus is creation and annihilation operators of the field. Also, we define the detuning of these frequencies. Okay, such Hamiltonian has the following eigenstates called rest states. One is the state with no excitations of the field and with the ground state of atom, and n plus states given in such way through basis states and n minus states. And that n is the following parameter. the corresponding eigenenergies to that state is the following. And to our goals, it is convenient to rename these sequences of eigenstates as jk and sk. Here the numeration will be from 0. Okay, let's take the minimal natural solution of such inequality. If we take that solution then we take such k0, then the tail of the sequence S with the indexes greater than k0 will be strictly increasing sequence. It will help us to construct the special type covariant states. Consider the partition of our space H into 3 direct summands, plus states, minus states with index greater than k0, and all other states. So also take 2 sequences of weights with same conversion conditions, strictly positive weights, and we suppose that weights are moments of probability densities. Okay, then through that weights, we can consider such, I think that it's called Gazo-Clauder covariant states that could be introduced by these formulas with such normalization factors. Also, consider the unitary group defining evolution of given the solution to our equation, Schrödinger equation, and consider free projections, orthogonal projections on our subspaces HK, and also introduce 2 families of orthogonal projections, one-dimensional orthogonal projections on these covariant states. And introduce also third projection, third family of projections. It's all of that projections are equal to H3. And then we have such an example. The subspace given by this rule with the same way, in the same way like the parameterized POVM in finite dimensional Hilbert space, such subspace is a non-commutative operator graph with the anti-clique EH3. Also, I want to give one more example on evolution of 2-dimensional quantum oscillator. Let us consider Schrödinger equation with such Hamiltonian, and let unitary group defining the evolution will be the exponent of that Hamiltonian, and then it is possible to define the orthogonal projection for which this subspace will be an operator graph, and it will have an anticlick. Solution of the Schrödinger equation, of that Schrödinger equation, could be given through covariant states. Consider the family of covariant states and their products. When we define such complete system of vectors in L2 of R2, we introduce the tensor product structure to that space. And this group could be given in that over complete system by this formula. Okay, also consider one more system of covariant states and such positive operator.
2 minutes left.
I don't hear you. Okay, then for this operator, such space will be non-commutative operator graph, and also it is possible to define the anticlicks for that graph. Moreover, maximal anticlicks. It's anticlicks maximal in a spectral parameter, in a spectral ordering. Okay, fix the unit vector in one in L2 and some orthonormal basis. And then if we define such vectors, then this projection will be a maximal quantum anticlick for proposed graph. Okay, I think that's all. Here is some links to our works.
We have 1 minute for discussion. Our next speaker is Grigori Amosov. He has prepared a talk. Tsirelson conjecture has a negative solution.
Yes.
You have half an hour. Let's go.
Okay. First of all, I would like to thank the organizers for this good opportunity to talk about maybe the most interesting results of the 21st century. This is about how to distinguish between two types of quantum correlations. If you can remember, the same result but of the 20th century is the Bell inequality that allows us to distinguish between classical and quantum correlations. And really it's very interesting. And the group of authors presented recently, by this year, the result concerning the property allowing us to distinguish between two types of correlation introduced by Boris Tsirelson, the man of genius, of course, recently passed. He was originally from Leningrad and from Israel after, and I will discuss at first what are correlations and why we can divide two types of correlations, and then I will discuss how the new authors solved this problem by Boris Tsirelson. And at first, spatial correlations, CQS, depending on parameters N and Q, are the following. Suppose that we have two sets, the resolution of identities acting on the same Hilbert space H. At first, these sets, you can consider only projections. These two sets depends on parameters A that indexed the observables, and X, this index means the value of observable. And we need two types of these sets, indexed by A and B. Then you can take a tensor product of A and B of such kind. So we have a set, we can obtain the set of probability distributions indexed by A and B and X and Y. It means that you have two observables, they are commuting because by a construction, commuting by a construction. And so we can measure these observables of special kind in some state psi from the Hilbert space of a tensor product. If you will think about classical correlations, you need to put here two types of functions. This is, will be the expectation, and instead this A and B, you need two functions, psi and eta, that at first the square of psi equals psi, the square of eta equals eta, and really it means that these two functions are indicator functions of some sets of the probability space you consider, and then you don't need the notion of tensor product. You only can put here two functions. They are commuting by a construction without any tensor product. So the question arises, what's about to put here commuting projections instead of projections that are commuting by construction, arbitrary commuting projections without using a tensor product. What will be? This is the point by Boris Tsirelson, and you can take two sets of projections indexed also by A, B, X, Y, but without any tensor product structure, and replacing the tensor product structure by the condition of commuting these two projections. Then you can construct the set of probability distributions P depending on four parameters, and for fixed psi belonging to tensor to a space, a Hilbert space H, without any tensor structure, and so here we can put here obvious product, a multiplication of operators, and this is close to the classical case, but here we have commuting projections, not functions, not indicators of some sets in the probability space. If the Bell inequality allows to distinguish between this set of P spatial correlations, when you have a tensor product and a product of two indicator functions of some sets. The Bell inequality allows to distinguish between these two cases. So the question by Tsirelson is it possible to distinguish between spatial correlation and commuting correlations? This is the question. This is the question of posed by Tsirelson in 1993, and I should explain that N is concerned to X and Y, and K concern the volume of A and B. So these are connected with a number of observables, and these are connected to a number of events of these observables. And this question is very, very deep, and only now it was solved. It was solved, and it was obtained a negative solution. So it doesn't take place. Spatial correlations do not coincide with commuting correlations. In 2219, William Slofstra, obtained the preliminary result. If you take a convex closure of spatial correlations, a convex closure, so you will obtain some set more than the previous set of all spatial correlations. The closure results in a new set. So really, these results gives us the information that the Tsirelson conjecture doesn't hold true. Nevertheless, what's about to compare the convex closure and commuting correlations? If we take here a closure, is it true that these two sets coincide or not? And I will discuss the negative solution to this conjecture. So recently, the group of authors you see on the screen proved that the convex closure of spatial correlation is not equal to the set of commuting correlations. You can see this paper in Archive. What is it? The main idea. Correlations appear as a result or the very deep results in the formal theory of languages. you should examine whether it's possible to answer for some formal string, whether this string belongs to the set L or not. And this examiner, some examiner, the same as verifier, should recognize between two issues that belongs to L or not. How to recognize in formal language theory? Is it true or not true in the other terminology? If Z belongs to L, so Z is true. And if not belonging to L, Z is false. Then some special possible construction for verification is multi-prover interactive proof system, MIP. Maybe you can recognize this approach as some process during the exam at university. Since the examiner has no enough knowledge to answer the question that belongs L or not, he asked multiple provers, in this context students, and after analyzing their answers, he make a decision, maybe with some positive probability. Is it true or not? So you have one verifier, the same examiner, and several provers, which can be recognized as students. In quantum case, considered by the authors, we have some more complicated structure, so-called MIP star. This is multi-prover interactive proof system possessing one verifier interacting with multiple quantum provers sharing entanglement. This protocol can be realized and really in experiments that we have with the verifying the Bell inequality, we have this protocol MIP star. And therefore, it's quite non-trivial result. They have proved that MIP star equals NE class in the theory of languages that are problems for Turing machine, solvable for Turing machine. It is the same, it's quite non-trivial that this MIP can be solved on Turing machine. Then MIP star are associated with spatial correlation. In fact, really all experimental protocol concerning to testing the Bell inequality, this give us exactly spatial correlations. But because their first proved that this is the same level of complexity as tasks for Turing machine, we have unsolvable problem for Turing machine. This is the so-called Halt problem. We ask if, as Turing had shown in 1936, if you ask the Turing machine whether it's possible to answer for some question for finite time, this is so called half problem. This problem is unsolvable for Turing machine. But because the authors of the article I discuss now had shown that MIP star is the same as the set of problems for Turing machine, so it's impossible to solve the hard problem for the MIP star protocols. So one verifier and several quantum provers sharing entanglement. So for this protocol, it's impossible to solve the half problem. Then so it's impossible. It's impossible to solve for MIP star, but as was shown, it's possible to solve using commuting correlations. And how it can be recognized, how the authors work with this very, very difficult problem. Some mathematics, what are we doing to show that it's true? The verifier asks provers the pair of questions, X and Y. Maybe you have forgotten what is. We have these sets of projections, commuting projections. X and Y concern the events for any resolution of identity, and A and B different sets of projections, different resolutions of identity. So the verifier one verifier asks the pair of questions, and K non-commuting provers, really it's possible to consider only the case K equals 2 and N also equals 2. It's enough. If you prove the results for this, the simplest case with N equals K equals 2, it's enough to prove the negative solution for the Tsirelson conjecture. The provers give their answers, and the verifier make a decision according a predicate. Predicate, this is the decision rule. If you have X, Y, A, and B, the predicate should send you 0 or 1. 1 means that it's true, and 0 that it's false. But you suppose that the pair of questions X and Y are given randomly with some probability distribution mu, and the procedure of examination is called a game G. Then the classical value of game is given by the formula. You have here the probability distribution mu, the predicate D, and these correlations. And suprema is taken over all admissible correlations C. So depending on the protocol, you can put here classical correlations or spatial correlations or commuting correlations. And surely that you will have 3 difference value depending of possible correlations. Since the whole problem for Turing machine is impossible to solve, then if you have here spatial quantum correlations, you obtain the value of game strictly less than 1. Strictly less. Really, it's immediately falls from the negative solution to the whole problem for Turing machine, but we have this inequality, and the authors have shown that if you take here commuting correlations, you can obtain the positive solution, and the value of such game equals 1. So we proved that the Tsirelson conjecture, has a negative solution. Moreover, about the closure, because determining this value, we take the suprema. Then, although here I put spatial correlation, nevertheless, it is the same if I put here the closure of all spatial correlations due to taking suprema. So it's very non-trivial, a very long paper, and with the deep, interesting results. And I suppose that surely this is maybe the main result of different from different results of 21st century. Maybe this is the best in quantum theory. Thank you for your attention. It's all.
Thank you. We have 4 minutes for discussion. Any questions, comments? Okay. As a sort of comment, I can mention what university examination is a sort of game too. Not only.
Yes. I mean, this is a joke, of course. Nevertheless, the same procedure with some probability.
Yes. You have 1 more slide.
Yes? Oh, sorry. This is the last slide about a new value of the game, this examination game. And now we can solve this game. So if we consider this protocol as the exam for student, so for this game you can test whether a student is good or not with the probability 1. In reality, it's not possible, only in quantum world.
Thank you.
Okay, thank you.
Our next speaker is Ashot Avanesov.
Yes.
Are you here?
Yes, I'm here. Can you hear me?
Yes.
Okay.
Next talk is geometrical and group properties of discrete analogs of center of mass and cluster tomograms.
Yes. So I can start. Can
Yes, you can.
I? Mm. Just a moment. So, can you see it?
Yes.
Okay. Let us start then. So, hello everyone. My name is Ashot. I'm from Moscow Institute of Physics and Technology. And today's talk is about theoretical problems related to the tomographic probability distributions in these probability representations. In these representations, the quantum states are described by genuine probability distributions. And though though this topic is theoretical, it can be connected with quantum state tomography, which is experimental stuff, and so on. So let's go, and shortly our work is about the construction of tomographic functions for QDITS systems that are these tomographic functions associated with linear manifolds in the discrete phase space. So I think that it will be good to tell a little about the discrete phase space and the discrete Wigner function. And I should note that it is various ways to introduce to construct the discrete Wigner function, and we will follow the approach of Wouters. So my presentation is divided into parts. The first part, in the first part, we discuss the demographic probability representations and the representation of quantum states for continuous variables quantum systems. In the second part, we will discuss QDIT systems, and we will discuss how to the discrete phase space formalism, and finally we will come to the main part of these presentations about the tomographic probability tomographic functions associated with different linear manifolds in the discrete phase space. So let us start from the beginning. The phase space description. Yes. So commonly classical states is described by a normalized non-negative function defined in the phase space probability density distributions, and actually quantum states also can be described by the function that is defined in the phase space. However, it is, for example, this the Wigner function. You can see the transformation from density operator to the Wigner function. However, the Wigner function is not probability distribution. Actually, it is quasi-probability distributions. Like probability distribution, it is normalized, and we can restore the density matrix from Wigner function and obtain every statistical information we want. For example, we can obtain from the Wigner function the probability distributions for coordinate and momentum. But unlike the probability distribution, Wigner function can take negative values. However, the state of quantum system can be described by the genuine probability distributions. For that, we can use random transform of the Wigner function. And this technique is used to random transform of Wigner function is actually probability distributions of outcomes of measurements of this observable. And actually, this technique is used in quantum state tomography for tomography of optical states. So from the values of this function, we can restore actual Wigner function, and subsequently we can restore the density operator. This function is probability distribution over this variable x, and it is normalized and negative, and also it is homogeneous. So let us go to the case of several degrees of freedom. For example, the composite system, multi-particle system, or multi-mode system, some optical states, I don't know, whatever. So in the case, the coordinate and momentum are vectors. Here we consider the vectors of size n. So the Wigner function can be introduced straightforwardly, and there is nothing interesting. But the tomographic function we can introduce by different ways. For example, we can introduce by this transformation. Here, the kernel of this transformation is a product of Radon's kernel of one-dimensional cases, of one-dimensional Radon transformation, and we see that this function has 3n parameters as its variables. Actually, we can use only 2n plus 1 parameters as variables, and it is as it is in the case of the center of mass tomogram. Here we can see the center of mass tomogram is integration of values of Wigner function over hyperplane of dimension or linear manifold of dimension 2n minus 1. Actually, for this we have one linear condition, and for multidimensional symplectic tomogram we have n linear conditions. We can use mixed strategy, and for example, for cluster tomogram, we have R linear conditions, and we divide the vectors QP, nu, and mu on R parts. And for every part, we use these delta functions and the product of the delta functions are actual kernel of this transformation. So I suppose that's all concerning the continuous variables case, and we can go to the qubit systems. So we should start from the discussion of the framework of the discrete phase space. So how can we introduce the discrete phase space? So actually, so we start from the consideration of qubits where the Hilbert space the Hilbert space has where Hilbert space has prime dimension has dimension which is a prime number. In the case, the discrete phase space can be introduced as a finite plane of size d squared. For example, for Q2, example of Q2 you can see on the picture that is in the right of the slide, and we can here you can see labels that that enumerate the rows and columns, and these labels are associated with eigenstates of operators x and z that was presented here. And also we use notations omega for this exponent, and we will use it later. So that's all. Also, we should talk about these displacement operators. They have for the case d is not equal to, we can present the displacement operators by these expressions. These operators transpose the point from qp to q plus delta q and p plus delta, plus delta p. In the key, so it has these expressions. This 2 to the power minus 1 is modular arithmetic, in modular arithmetic, and That's why this expression is not suitable for qubit case. In qubit case, the displacement operators are actually Pauli matrices. So how can we introduce the Wigner function? We introduce the operators A. In literature, we can in literature we can find the term Wigner operator, and we use trace transformation from density operator, and we obtain this Wigner function. And if we consider the case of the prime odd number, the Wigner function can take, and we make some derivations, we can come to the expression that looks very familiar to the continuous to its continuous counterpart. Okay, so we have discussed how to construct the Wigner functions for prime dimensional qubits. However, what should we do in the general case? General case, D is a composite number. However, we can present it as a decompositions of prime factors, and the discrete phase space we can construct as a Cartesian product of D1 squared plane of the finite plane of size D1 squared and finite plane of size D2 squared, and so on. In the case coordinate and momentum are vectors, and this case it looks like the multimode or multi-particle case from the continuous from the consideration of continuous case. So and the Wigner operator here is introduced as a tensor product of prime dimensional Wigner operators. However, we do not consider the general case, and we do not want to construct we don't construct our tomographic functions for the case of general Hilbert spaces. We just consider the cases of prime of power of primes dimensional Hilbert spaces, and in the case the Wigner operator can be presented in this form, and here all operations are made in modular arithmetic, and the discrete phase space is actually a vector space over finite field, because D is a prime number. And also we can present the displacement operator as a tensor product of displacement operators of prime dimensional Wigner operators, prime dimensional cases. So that's all what I wanted to tell you about the discrete phase space formalism, and now we can move to the main part. So as I mentioned, we consider only the cases of Hilbert spaces of dimension of power of prime dimension, and in the case the discrete phase space is a vector space over a finite field, and here we can introduce the discrete center of mass tomogram as a sum of discrete Wigner function values over 2n minus 1 dimensional linear manifold, as it was done in the continuous case. This we prove that this function is non-negative, that it is possible to restore the density operator from these function values, and Also, this function has the general properties that is as any tomographic function is non-negative, normalized, and homogeneous. And also, we find that these tomogram correspond to projective measurements, and it is a probabilities of obtaining outcome kappa, and the measurement is determined by the vectors mu and mu. The expressions for these operators pi you can see in the bottom of the slide, and also I should mention that this is a projective measurement. So we have introduced the center of mass tomogram as a sum of Wigner function values over the linear manifold of dimension 2n minus 1, and we used one condition for that. So we can use more condition and construct the function that is associated with linear manifolds of lesser dimensions. So for that we consider the matrix gamma. We consider the matrix gamma of size m times 2n, and this matrix has linear independent rows. And so this matrix determines some linear manifold, and we can construct the functions. We do not know whether it's non-negative by this way, by the sum of Wigner function value over this linear manifold. However, unlike the discrete center of mass tomogram, these functions does not automatically have the properties of non-negativity, property of non-negativities. For example, we can consider the case of where matrix gamma have 2n rows, and that's why we in the case this value of this function will be equal to some value of Wigner function, and we know that Wigner function is not necessary. The value of Wigner function is not necessarily non-negative. So we should find the conditions for this function to be non-negative. So how should we for this? We should rightly choose the matrices gamma. Actually, for this we use this approach. We presented this approach. We presented this function as a trace transformation of density matrix, and we searched the conditions for these matrices pi to be non-negative, and we found this condition. You can see this condition in this green box. However, this condition only for the case when d is not equal to. The case of d equal to, I call multi-qubits. Maybe it's not a good term, but later I will use it. But in the case, all the cases except multi-qubits cases, this condition is sufficient for the function w function w is non-negative. So actually, moreover, if these operators non-negative, they must be projectors, and they determine the projective measurement. This projective measurement is determined by the matrices mu and mu, and outcome, so this measurement is encoded by vector kappa. Vector kappa has size of has m elements. Okay. What we also notice that these conditions that was in this green box, also these conditions mean that these elements, these displacement operators, the set of displacement operators, they described by these expressions, parameterized by this Ash vector, or vector Ash, form a commutative group of dimension dm, and we also have some correspondences that every group of these displacement operators corresponds to unique to n minus m dimensional linear manifold, and every matrix, group matrix I mean, that has linear independent rows and the conditions in green that I presented 2 slides ago holds, then this matrix corresponds to the set of generators of the group. Actually, these statements also can be applied in the case of multi-qubit states. We didn't find the conditions like we did like the conditions for the case, but maybe these statements will help us. However, it is not done yet. It hasn't done yet. Okay. And we also finally we present the restoration formula for the Wigner function values. Actually, we just need to know. We just need to this formula for that denote this number, this n, that denotes the number of good matrices, and we can show that this number is 0 for the cases when m greater than n. It means that it's not possible to consider a negative function in the case, which is quite which is what we expected, and it should be there. And in the case of m lesser than n, we obtain these formulas. I don't know, just present it here. So to summarize, what have we done? So we actually investigated the possibility to construct demographic functions that associated with linear manifold, and these functions was obtained as a sum of Wigner function value over these linear manifolds. And it turns out that for most of the cases we should rightly to choose these manifolds, but we managed to construct these functions for the cases of all cases except multi-qubit cases, and the cases of d equal 2 should be discussed in the future, of course, maybe by using the group properties that we also found. Okay, that brings me to the end of my presentation, and thank you very much for your attention. If you have any questions, I will try to answer them.
Thank you for your talk. Any questions, comments? Ashot, what was omega in your presentation?
omega.
Small omega.
Oh, this I told it about this. Yes, you asked me about this omega.
Ah, yes, yes.
Yes, it's just
okay.
exponent.
Thank you.
Mhm.
So you, why D have to be prime? Is it essential or it just?
It is essential. Okay. Just you can see these expressions, and it is essential because we do not the elements of vectors Q, P, mu, and nu must be the elements of the same field.
Why field? You have multiplication, summation, but I don't see.
No, I use modular arithmetics to describe.
If D is not prime, you have not field, but
Okay.
it seems to be enough.
Okay, you mean the case when Hilbert space when D to the power n, but D dimension, but D is not prime.
Yes.
Yes, it seems to be enough, but the calculations become difficult, and I actually didn't do this. It seems that it's possible to introduce this function for the case of D is not prime.
Actually, I think there is some connection with our next talk, which is presented in program as mine talk, but I am not a speaker. The speaker is my student, Aleksandr Mokeev. Okay, any other questions to speaker? Thank you, Ashot.
Thank you very much for.
When Aleksandr Mokeev, are you ready to present our talk?
Good afternoon. I think yes, I'm ready. Now I'll try to demonstrate the screen with presentation. A minute. So, I think I can start.
Yes, you can start.
Okay. First of all, I think I have to thank all the organizers and members of the conference for this opportunity. I'm here today to deliver a presentation called Ternary and Binary Representation of Coordinate and Momentum in Quantum Mechanics, which was done under the leadership of Mikhail Ivanov. It's based on the original paper about the binary representation, but during the work with ternary ones, we have found some interesting facts, and it helped us to understand the binary case better. So first of all, I'm going to say about a pair of words about the possible applications of this representation. Then I will introduce the objects which are used to build this representation. I will speak about the lattices and an operator of the cyclic shift over the lattice. And finally, I'm going to give information about the results of our work, which are numeral systems and digit operators, some renormalizations, commutation relations, and finally, we're going to speak about integral ternary representation. So, first of all, as I've promised, we're going to speak about possible applications of this representation. First of all, the most obvious one is that for simulation of any quantum or classical systems on a quantum or classical computer, we need a discretization of coordinates and momenta, and that's the way to make it. The other thing is that during the building of this representation, some renormalizations emerged in quite a natural way, which can be interesting in the context of quantum field theory, for instance. First of all, I'm going to introduce you a Ternary lattice. We have a lattice for a coordinate and a lattice for momentum. Here you can see some properties of these lattices. I don't think that we need to concentrate on it a lot. Here I have to mention that we have two ternary systems, which are going to be called non-symmetric one with digits 0, 1, and 2, and a symmetric one with digits 0, 1, and -1. Then we are investigating not only ternary but also binary systems. Then we need binary lattices, which are built simply the same as ternary ones, with only difference that we mainly have 2 instead of 3. And we are also going to speak about 2 systems, about a non-symmetric one, which was introduced in the original paper of Mikhail Gennadievich, the link on which will be at the end of the presentation, and a non-symmetric one with digits plus minus a half. The lattices are...
In a binary symmetric system, we have different lattices.
Yes. For a binary symmetric system, we have a different lattice. Here you can see the lattice for a binary non-symmetric one, but later we are going to speak about binary lattices a bit more, and then we would be able to see the difference between the lattices. Yes. The lattices are periodic, which we can see, and we can say that the last node is glued with the first node of the lattice, so it's something like a ring. We are defining the quasi-momentum or momentum operator as a generator of cyclic shift. Here we can see how does this cyclic shift work. And it's important to say that we have an operator of minimal shift, which is a shift on a lattice constant, and any other shift can be obtained from the minimal shift as a power of it. So let's turn to the object of our work, and we'll start with a ternary non-symmetric system. Here you can see an operator of momentum digit, which is calculated. So here you can see it, and there I have to mention that we can see a picture of digit number 0. Digit number s can be obtained from it with scaling the x-axis in 3 in the power of s, which means that the ladder for digit number s will be longer for 3 in the power of s. If we want to represent the negative number in this system on the line, we will have some problems, because on the real line, the highest digits of all the highest digits of this starting from a particular one will be equal to 2, which means that we will face a divergent sum.
For negative numbers.
Yes, for negative numbers. How to solve this problem will be discussed later. So now I have just to mention it. The second system we have examined is ternary symmetric system, for which we have also calculated the digit operator. Here it's interesting. Then in this case, we can see that such problem doesn't emerge because the highest digits for both positive and negative numbers are equal to 0 on the line, which means that the renormalization is not needed for this system. So here you can see some examples of operators which were calculated explicitly. These are just examples. Here it's interesting that, for instance, for a momentum operator for non-symmetric system, we can see that this operator has not a sparse matrix, which means that it's not local at all, and it helps to to keep some symmetries of the theory if we want to apply this representation to some simulations. Then you can see the same one for the symmetric system. The matrix is also not sparse. And now we are turning to the binary systems. There you can see the original binary system from which all these things started. For this system is also calculated the digit of momentum. And here we want to speak a bit more about the lattices. First of all, you can see the lattice here and the plots of a digit on this lattice. With the green circles, we have digit number 0, and with the blue circles, the digit number 1. There we can see how does this scaling work with the longer letters. And then we'll turn to a binary symmetric system, which can be obtained from the binary non-symmetric system with a shift over the y-axis on minus one half, and shift over the x-axis for a half of the lattice constant. So this shift on a half of the lattice constant means that 0 is no longer a point of the lattice. We have no node here, and it's also quite interesting. There I also have to mention that analogous to non-symmetric ternary system, for the symmetric binary system, we will need renormalizations for both negative and positive numbers. This brings me to the part about the renormalizations. We have seen that we need to do something if we want to assign a finite value on the line to negative numbers in the ternary non-symmetric case, for both negative and positive numbers in the binary symmetric case. And so the way to do it is to use, to apply the formula for a convergent geometric progression to a divergent geometric progression in order to assign a finite value to a divergent sum. the way to make a general formula for negative and positive numbers is to use a formal equality. X is equal to 3x minus x divided to 2, which can be rewritten in the following form. And this solves the problem because, as we have seen, the highest digits of x from a particular one will be all equal to 2, which means that we are going to have 2 minus 2 for the highest digits here, and the row is going to converge. For the binary case, we can use the same renormalization with only difference that then we exploit the equality that x is equal to 2x minus x. Now we want to say a pair of words about renormalization of sums on the lattice. Here we have to say what renormalization on the lattice is, because it's quite clear that any sum on the lattice has to converge, because we have only a finite number of values in it. But it's the way to switch between the representations of the ring Zn, or to switch between the representations of the lattice. Originally, we had only positive nodes in our lattice, but we can also have a lattice which has as negative nodes, not only positive, but also negative nodes. If we want this system with these lattices to work, we need this renormalization to assign to the last digit of our system a value -1 instead of 2. And this will lead to the following renormalization. And now, when all the operators were calculated and we have seen the explicit equation which describes them, we can now calculate the commutators of for starting with the digit-digit commutator and then go ahead. So the analysis of a digit-digit commutator gives us the result that fractional part of the momentum commutes with the fractional part of coordinate. The highest digit of momentum doesn't commute only with the lowest digit of the coordinate, and vice versa. Afterwards, we have calculated the coordinate momentum commutator on the lattice. Here we can see them. And then on the real line. Here it's quite interesting to say that both binary systems give us the same result. Which is because the binary system, as I have said, symmetric one can be obtained from the non-symmetric one with a shift. The shift on a constant over y-axis does not affect the commutator, and the shift over the x-axis becomes infinitesimal in the case of real line, because the lattice constant is going to 0. So now now we want our commutation relations on the line to meet the canonical commutation relation. then we would need to demand some formal relations to implement in order to meet this canonical relation. I think I will start with the non-symmetric one, for which we will define a set A with 3 as a set of numbers whose ternary expansion contains a finite number of non-zero factors with negative powers of 3. And then we have to demand the following expression to be true. This expression looks quite natural if we think about such expression for Fourier transform, or when we are assigning the integral of such exponent to 0. Then for the symmetric system, we can define one more set, A3 with prime, which looks a bit more complex, because then we need to conform a number A such that product of A and 3 in some power is A. So then we also can build a renormalization for this system that will lead to the commutator meet a canonical relation. And finally, we are going to speak about integral ternary representation. It's quite interesting because, first of all, it's scaling invariant, so it does not change with the changing of scale. Yes. So if we want to work with non-integer values of numbers of a digit, then instead of sum, we have to write an integral. Okay. For positive x, as now we are speaking about ternary non-symmetric system, and then for positive x, highest digits from this value to are equal to 0, and we can show that this such integral does not only converge, but also gives a right value that this is not our demand, it's just a general formula. For negative numbers, we need to define the renormalized integral, an integral with a prime. We can make it as we did before with the sums, which will lead to the following expression. And on the other hand, we can make a renormalization by integrating by parts and omitting the divergent summand. So we are making it. And here, this is a semi-constant, not semi, partially constant function. And then instead of this integral, we will get a sum of delta functions. And this will lead to the following equation, which also gives us right result. So I think it's time to sum up what I have said before. First of all, the main idea of the work is that instead of coordinate and momentum, we can consider the digits of coordinate and momentum as observables. Secondly, I have to say that while constructing these representations, we have met some renormalizations which occurred relatively naturally. And finally, we have got an integral representation which exploits integrals instead of sums and is scaling invariant. So now it seems to be all I wanted to say. Thank you for your attention. And here is a link to the original paper of Mikhail Gennadievich. So.
Thank you, Aleksandr. Any questions, comments? Okay. As a co-author of this talk, I can give some comments. Instead of two observable with continuous spectrum, coordinate and momentum, we consider just a set of binary or ternary digits. And it is interesting that we have automatically some renormalization rules. And these renormalizations works not only for numbers, but also for operators of coordinate, operators of momentum. And as additional bonus, we found that if we consider binary or ternary expansion, usually we consider a power series. But instead of power series, we can use an integral with the same integrand, and it can be useful from the point of view of symmetry. If you consider power series, you have some scales which are special. It is a unit and unit times powers of 2 or powers of 3. In the case of integral, instead of sum, all scales in some sense are equivalent. So it's the end of my comment. And if you have no additional questions, then we have a lunch break up to 4 p.m. Thank you for attention.